Hello everyone, Mr. John here from Areteem Institute with this week's Thursday tidbit on special right triangles. These are typically just called special triangles, but they are going to be right triangles, and that's going to be important because we need to be using one of our most famous theorems about right triangles, the Pythagorean theorem. So if you need a quick review, if you want to see the proof of this again, you can check out the Thursday tidbit from the past in the video link below. Otherwise, we're just going to be using this theorem today. And importantly, it tells us about the lengths of the sides. If you have two sides, length A and B, then that hypotenuse is C squared is A squared plus B squared. So it allows you to say something about the lengths of these sides in a right triangle. Now, what is the simplest right triangle? The simplest right triangle is an isosceles right triangle. My header here has a little bit of a spoiler, but just if you think about a isosceles right triangle, that means that, okay, one of the angles is 90 degrees, so what are the other two angles? They have to both be 45 degrees, right? So both of these other angles are 45 degrees in this case. So that's important because now, right, we have this 45, 45, 90 triangle. That's where the name comes from for this special triangle there. Now, two smaller sides. A squared is 1 squared. B squared is 1 squared. C squared is the missing side, right? So this is our kind of C squared there. 1 squared plus 1 squared is 2. So 2 is equal to C squared. So our missing side here is square root of 2. So our hypotenuse of this triangle is square root of 2 in this case. Now, why is it called a 45, 45, 90 triangle? Why don't we call it a 1, 1, square root 2 triangle? Well, remember your similar triangles ideas, right? Any triangle with angles, 45, 45, and 90, will be similar to this triangle right here. So the sides will be in ratio 1 to 1 to square root 2. So this is something we always can kind of keep in mind. Anytime you have this kind of 45, 45, 90 triangle, the key thing you can think of is that to get from the legs to the hypotenuse, you have to multiply by square root of 2. So if you change that 1 to a 4, then you have to multiply by square root of 2 and you get 4 square root of 2. You can go back and forth in these similar triangles for other lengths. And that's why the angles are the most important here, and we call it a 45, 45, 90 triangle in this case. There is one other big special triangle, and this is called a 30, 60, 90 triangle. Right, so here we're giving you the angles. We can't just call it isosceles. Of course, if I tell you one of the angles, if you have a 60-degree angle in a right triangle, the other angle has to be 30 degrees, of course, because those angles add up to 180 as well. Now, if we think about this kind of as a puzzle piece, right? We think about this 30, 60, 90 triangle. We like that 60-degree angle. You might kind of remember an equilateral triangle, which has 3 60-degree angles. So what happens if we kind of draw that in here, right? What if I put another copy of this, so an identical copy of this triangle, and turn it into an equilateral triangle here? So we kind of flip it over. We have another side of length 1. We have another 60-degree angle over here, of course, because we're turning this into now an equilateral triangle, because we have another 30-degree angle at the top. So the idea is we're then doubling this there. Well, we have 3 60-degree angles, meaning that all the sides are the same in this case. So we have a 2 and a 2 for these missing sides, right? Just from an equilateral triangle there. So now we're ready for our Pythagorean theorem business. So we have 1 squared. Be careful because now the missing side is in the middle. So let me say 1 squared plus b squared is equal to 2 squared in this case. So we have 1 plus b squared is 4, so b squared is equal to 3. And therefore b, which is the height of this triangle, is square root of 3. So in this case now we have this 30, 60, 90 triangle. And again, you can think of these as ratios because we could make this bigger, smaller. All of these are always ratios in this case. But for a 30, 60, 90 triangle, we have sides in ratio 1, square root 3, and 2. Okay, these are the two big ones. These are kind of our nice angles, and these are typically what we refer to when we say special triangles. You could name them the 45, 45, 90 special triangle. That one is the one here on our left. So we have the isosceles right triangle with sides in ratio 1 to 1 to square root of 2. And then similarly, we have our 30, 60, 90 special triangle, which is half of an equilateral triangle, and this has sides in ratio 1 to square root of 3 to 2. Always remember, right, the small side is across from the small angle. So the 1 is across from the 30 degrees, the square root 3 is across from the 60 degrees, etc. there. And so these types of ratios are very, very helpful in questions about triangles, or even questions that can be turned into questions about triangles as well. Let's look at our example here. In quadrilateral ABCD, AB equals BC equals 4. So these are already labeled in this diagram below. We have then angles given as well. So angle A is 75 degrees. Angle B is 90. So let me label the 90-degree angles right off the bat. C is 105 and D is also 90 here. So here we have now the information about the right angles labeled here, and we want to find the area of this quadrilateral. Now, what should jump out at us here? We have 4 and 4 and a 90-degree angle. So wait a second, what happens if I connect A to C and now form a triangle? What do we know about this triangle? Well, it's an isosceles right triangle. So these angles here must be 45 degrees and 45 degrees. And we know, and this is the important part for finding information about the areas, we know that this now has ratios 1 to 1 to square root 2. So remember, we find the hypotenuse by multiplying by square root of 2. So this AC length is 4 square root of 2 in this scenario. Now, let's start thinking about the angles that we have left from here. So angle A is 75 degrees. Well, part of that angle is 45, so the other portion has to be 30. Hey, that's looking good. 45 plus 60 is 105, so the other portion of angle C, when we break it up, is 60. So now ABC was our 45, 45, 90 special triangle, and now ACD is a 30, 60, 90 special triangle. So we know the longest side is 4 square root of 2. So the smallest side is half of that. Remember, 1 square root 3, 2. So half of this is 4 square root of 2 divided by 2 gives us 2 square root of 2 for CD. And AD is square root of 3 times this. So you could write this as 2 square root of 6. But remember, you could also just keep this separated as 2 square root of 3 square root of 2. That's not simplified, but right, I will kind of see, we can see why that might still be helpful in this case. Now, we can break up the area into the pieces here. So we definitely have two pieces to look at. So we want to know the area of ABCD. Well, what about triangle ABC? Triangle ABC, well, this is clearly 1/2 times 4 times 4. So that is just 8. That one is pretty easy to calculate here. 16 divided by 2 is 8. What about triangle ACD? So this is where almost even leaving it unsimplified is a little bit easier. So we have 1/2 times 2 square root of 2. So right away those 2's cancel. And then we have times 2 square root of 2 square root of 3. Now why am I writing it this way? Well, now we can combine the square root of 2's. Square root of 2 times square root of 2 is 2. So we have 2 times 2 times square root of 3. So right, just in that case then, we have 4 square root of 3 for this triangle there. So what is our final answer then? How do we find the entire area of ABCD? Of course, we just need to add these pieces together. So there's not too much simplifying we can do here, right? We just need to add the two triangles together. The second triangle has a square root in it, so we can't combine it at all, but that's still our area. Our area is 8 plus 4 square root of 3. You could go in a calculator and find the decimal approximation if you wanted to here as well. Remember, we have a summer camp coming up at Areteem. So this July, we have 4 weeks, algebra, geometry, counting and probability, number theory. It's a great way for some supplemental learning, some math contest prep, right? Getting exposed to new ideas in math for kind of middle school and high school kids. Information is in the link below. There's still time to join, right? It's an online camp, so you can join and, right, fill out some information and get started right away once the camp starts. And I hope to see everybody there. And as usual, check back each Thursday for a new math tidbit. Check out ziml.areteem.org for more daily math practice and other resources, contests, a community there as well. But as always, right, please like and subscribe in the links below, and I will see you all next week. Goodbye.